is on the lattice formulation of LPC coefficients. So, over the past few classes we have been discussing about the different approaches in order to compute the LPC coefficients. Okay. The problem we posed few classes back, but then we had seen that essentially the challenge lies in trying to obtain the optimal set of coefficients which will be based on the observation based on the speech, and we have been discussing few methods such as the covariance method and the correlation based method, autocorrelation based method. And there we had seen that essentially the approach gets into an iterative one, so that one can compute in an efficient way all these coefficients alpha k's, okay, where k varies from 1 to p. So, essentially we are obtaining the first set of estimates, and then we are updating our estimates with iterations, and at the end of the pth iteration we are getting the final coefficients, okay, which we have to use. Now, this involves, as I said, that this involves two basic operations. First is that we have to determine the correlation from the observed speech waveform, and the second stage is that we have to do the matrix operation, okay, in order to determine the LPC coefficient. So, these two are involved. Now, there is a methodology which we are going to call as the lattice formulation, where these two approaches would be treated in an integrated manner. That means to say that we will not be having any explicit computation of the correlation, but rather we will be determining the LPC coefficients in terms of the prediction errors, okay, and we will be describing the technique pertaining to that very shortly. So, before we begin the lattice formulation, let us go back to what we did in Darwin's algorithm, okay, for the autocorrelation, okay. Remember that for Darwin's algorithm what we were doing is that the set of coefficients which we were calling as alpha j, okay, the set alpha j, and we were writing it as alpha j with the superscript I, the superscript indicating the iteration number. So, we were writing the set of alpha j I, and this j was in the range of 1 to I, right. This was the set that we had, and the significance is that all these coefficients are the ith order optimal linear predictor, okay. So, we are having only up to I. So, in the ith iteration of prediction we are having only ith order of prediction, I past coefficients. So, in the end we are going to have p, I is equal to p at the end, and there we will be having alpha jp as the last estimate. So, we have already seen that, and using these coefficients, that means to say that using this ith order predictive coefficients, okay, it is possible for us to design a filter, okay, and let us give the filter expression like this, that we are going to call that filter in the z domain, we are going to call that as AZ, okay, and we are going to write the filter A of z as 1 minus, and then we express this as the summation of alpha k superscript I into z to the power minus k, and this index k here changes from 1 to I. So, essentially what we have written is that I mean again with this ith order prediction, okay, we are expressing the filter. So, this is just a filter. I mean let's imagine that somehow we are able to realize a filter using this alpha k's, okay, using this I mean prediction parameters alpha k's, we are able to design a filter like this, okay. Now, in this filter, if we are giving a speech segment as an input to this filter, then what would you expect at the output of that filter? This is a filter realized out of the prediction coefficient. So, what I am asking is input is the speech segment, okay. So, we call the speech segment. So, the input to the filter is the speech segment, and we are going to write it as S suffix n of m, okay. So, you know that what we mean by this expression, that suffix n and within parenthesis when we are writing m, that means to say that we are going over to the nth sample, and then we are going to have m as our variable index, okay, and that segment we are going to write it as S n plus m into W m, where W m is the windowing coefficient, right. So, so essentially S n of m is the windowed version of the segment, and again for simplicity, instead of writing every time the segment with the subscript n, okay, we are going to write it as S of m. So, what we are writing here as S n m, we can simplify that by writing S of m by just simply dropping this subscript m. Now, if S of m is the input to the filter, okay, the filter as defined above, what would you expect at the output of the filter? Any answer? See, what is this filter? This filter is realized out of the predictor coefficient. Have you come across this filter expression in one of the previous lessons? I believe you have. I mean, the lesson which we had started, I mean, when we had started this linear prediction, linear predictive coding, there we had come across an expression like this. So, correct, that is it. So, whenever we are giving the S of m as an input to this filter, we will be getting the error, or rather the prediction error at the output. So, we can write it in the time domain expression, we can write the prediction error to be like this. In fact, the prediction error also we will be normally writing it as E n with the superscript I, E n I m, that is how we are going to write, okay. And again for simplicity, we will be dropping this superscript, this subscript n, and we are simply going to write it as E I of m, right. So, which will be the ith prediction error. So, the prediction error naturally whenever I am writing it with a superscript, that means to say that the prediction error will be iterative. So, the output to the filter will be the prediction error, and we are going to write it like this, okay. So, let us say that let us number the equations. So, the first one, the filter that we realize out of the predictor coefficient is the equation number 1, this Z transform expression of that, this we are calling as the equation number 1, and as equation number 2 we are going to write the expression for the error term. So, the error expression will be E I m, and that will be written as S of m minus summation k is equal to 1 to I alpha k I s of m minus k. So, this directly follows. I mean, you can just have a look at the expression. I mean, this is in the Z transform domain. So, which means to say that when you are back again to the time domain, okay, this Z to the power minus k is there, which will introduce k units of delay, which gets expressed as s of m minus k when we are back again to the time domain. Okay. So, this is what we are having. So, this is the prediction error, and now this we are going to call as equation number 2, and let us take the Z transform of equation number 2. So, what are we going to write? In fact, I mean taking the Z transform, we can write it as, now we are going to express it as the capital E I of Z. In fact, we did not have to use this at all, because we know very well that E I of Z is going to be A I of Z, okay, that is to say the filter times S of Z. So, which means to say that the filter that we have is simply like this, that here at the input we are going to have S of m, okay, and then we have a filter over here whose function is A of Z, if we say, okay, and then the output of that will be E of m, okay, or rather to say in the Z transform domain we are going to write it as E of Z, and here it will be S of Z, okay, the corresponding Z transform version. So, that in the Z transform sorry I mean I just wrote it in the other place, wrong place, S of Z and here E of Z. So, that E of Z, it will be nothing but A of Z into S of Z, okay. So, this becomes our expression 3, right. Now, again our objective will be to express the relationship in an iterative form, okay. So, in order to do that, let us go back to Darwin's relation, okay, what we were discussing in the last class, and as per the Darwin's relation, okay, remember that we had written this kind of an expression, that alpha j I, the ith estimate of the predictor, we were writing as alpha j I minus 1 minus k j alpha I minus j of I minus 1th iteration, okay. This is what we had written for the alphas recursion, okay. This is a recursive relation we got for the alphas. So, now what we are going to do is that we are going to put this expression of this alphas, okay, in, we will be putting it in the equation number 1, right. Equation number 1 is this, of course, equation number 1 is written in the Z transform form, okay. This gives the filters Z transform form, but in place of this alpha k I, we are going to write this expression, which means to say that the ith prediction will be expressed in terms of I minus 1th prediction and this residual term, that is what we have to do. And again, let me tell you, I mean although I will not be doing it in that details, but I leave it to you for working. What you can play with this equation number 1 is that you can express this equation number 1 as 1 minus summation k is equal to 1 to I minus 1, and make it alpha k I minus 1 z to the power minus k, and then you get another term which will be the ith, the last term of the expression, which will be alpha I, okay, into z to the power minus I, okay, just replacing k by I, you get the last term. And now this alpha I what you are getting, to express this alpha I, you just make use of this expression, you get this alpha I previous, and then you get alpha, and then you get this expression, and then again in order to get this you substitute the I minus 2th prediction and so on. So, in that process, okay, after doing the manipulations accordingly, okay, in order to play with the recursive relation, actually you have to know the art of playing with the recursive relationships. Some students are quite good in that. Okay. So, if you can play well with those recursions, ultimately what you are going to get is a recursive relation something like this, AIZ, okay, that can be expressed as AI minus 1 Z, okay, minus KI Z to the power minus I. See, I mean we can immediately note that how this Z to the power minus I term will come. This is after isolating the last term in the summation process, we are definitely going to get a Z to the power minus I term, and then with a proper I mean by properly identifying, you will be finding that this becomes AI minus 1 and the argument of this becomes Z to the power minus 1, and this is very interesting. Here is a Z to the power minus 1 term, okay, as an argument of this AZ. Here it is AZ, here it is AZ, but here it is AZ to the power minus 1, okay. By simplification, I mean by properly working, this is what you will be obtaining, and this will be, I mean, something which will become a very interesting, and more interesting will be in the time domain. Very intelligent students may be able to guess what is it leading to. Can anybody prematurely guess it? What is it leading to? Z to the power minus 1. Okay, then let us wait for a while. We will see the, I mean, great thing that this Z to the power minus 1 is going to do. Now, this is expression number 4, and substituting 4 in the equation number 3. That will be a very simple equation. In equation number 3 is the simplest equation, which just expresses the error in terms of this AZ and SZ, and if I substitute this equation number 4 into that, simply what results is, what we are going to do, EIZ is equal to AIZ SZ. Now, in place of AIZ, we are going to write simply this. So, what simply results is that it will be AIZ SZ. So, that means to say AI minus 1 Z SZ minus this expression times SZ. So, let us write it down. So, substituting 4 in 3. EI of Z, okay, is equal to A I minus 1 Z SZ minus KI Z to the power minus I A minus 1 argument Z minus 1 S of Z, right. So, this is the expression, and let us call this as equation number 5, all right. Now, what is the first term of this? What is the first term of this expression? Right. The first term is nothing but EI minus 1 Z, because it simply results in the prediction error for I minus 1th predictor, okay. And then there is a, I mean, it's not just the I minus 1th prediction error, but also there is something more, okay, a term like this with that interesting Z to the power minus 1. And let us just make a introduce, I mean, just define a term. Let us say that we define another filter expression, say Bi of Z, we write Bi of Z we define as this expression Z to the power minus I AI with an argument Z to the power minus 1 S of Z, okay. So, this expression what remains over here is this expression, and this we are calling as Biz. Okay, of course, here it is I minus 1. So, then automatically this will become Z, this will become Bi minus 1. Of course, that would mean that there is another term which will be there, and that will be Z to the power plus 1. Anyway, ultimately, I mean, if you are taking the inverse of this, so say this is equation 6 and taking the inverse transform of 6, taking the inverse transform of 6, in the left hand side we are definitely going to have, I mean, call its inverse transform to be small b I. Now, instead of z we will be writing m, because we are back again to the time domain, and this becomes equal to s m minus I minus summation k is equal to 1 to I alpha k I s m plus k minus I. Yes? Non-causal system. Yes, good observation. Okay. Any other observation? Delayed version. Would you call it as delayed version really? Or would you call it as advanced version? Delayed version is of course very understandable. I mean, when we were doing this alpha case, okay, the way we use the alpha case and we were generating the error, that error is a prediction error which we are going to call as the forward prediction error, right. Now, there is a great deal of similarity between, call it as equation 7, between equation 7 what we wrote over here and between equation 2. Just let us have a look at equation 2. And now you see, now you try to find out the similarity between equation 2 and equation 7. Both are quite similar expression, that there is an S term, okay, and there is a prediction term, summation k is equal to 1 to I alpha k, those things are remaining the same. Only thing is that here there is Sm and the predicted versions are Sm minus k. The samples which are being used for prediction, those are Sm minus k, and k is a positive quantity. So, which means to say that we are going back, we are taking the past samples to predict, okay, Sm, right. So, we are using the I past samples to predict Sm, and in that process generating a forward prediction error EIM. And what we are doing over here is just something which is opposite. Here it is Sm minus I. So, it is as if to say that we are going to predict Sm minus I from Sm plus k minus I, and k again is a positive quantity. So, that means to say that we are going ahead in time. So, based on the future samples, we are going to predict the present sample, something like this. So, in this case it is a backward prediction error, and because it is a backward prediction error, we will be denoting, we are denoting this by B. So, E we are reserving for forward prediction and B we are reserving for backward prediction. So, there is a backward prediction, there is a forward prediction. Now, it may seem to be puzzling, as one of your friends immediately expressed the apprehension that it is getting into non-causal. Yes, it is apparently becoming a non-causal in the sense that we are using the future samples. So, it is definitely in that sense a non-causal, but okay, it does not matter, it is realizable, because what you have to do is only to introduce delays. If you introduce some delays, then the same set of samples could be used to predict a past one, and same set of samples could be used to predict a future one, right. So, let us now leave with the mathematical juggleries, okay, without going too much into the nitty-gritties of it, but realizing that the physical significance that emerges from it is that we have to deal simultaneously with both forward prediction error and also with the backward prediction error. And now what we are going to do is that I mean the prediction error, now we return to this equation, I mean we call this as so this is our equation number 5, and if we return to this equation number 5 from here, okay, the or rather to say I mean you can say that if we go over to, in fact, equation number 2, because equation number 5 is in the Z transform domain. So, better you look at the equation number 2, which is already in the time domain. So, there what we can do is that there is a summation term k is equal to 1 to I. Instead, if you are taking I minus 1, you will be observing that essentially we will be able to identify the E of I minus 1 m, and in fact, I mean it can be shown that the prediction error sequence E I of m, that can be shown as E I of m can be written as E I minus 1 m minus k I b I minus 1 m minus 1, okay. This is going to be the equation number 8, right. So, this is we are getting it by just simple mathematical jugglery, nothing great about it, but very interesting fact that emerges is that the forward prediction error, the ith forward prediction error is expressed in terms of I minus 1th forward prediction error and I minus 1th backward prediction error, right. Now, what we can do is that just, I mean this is the time domain expression, and if we now substitute the equation 4, okay, equation 4 is this one, okay, if we substitute in 6, substitute in 6 means what? In 6 we are having this ai z to the power minus 1, this form. So, if we, instead of writing ai z to the power minus 1, if we derive it from this equation number 4, then what results is that, so substituting 4 in 6, what results is bi of z, that becomes equal to z to the power minus I, a I minus 1, z to the power minus 1 s of z minus ki a I minus 1 z s z, okay, and we are going to call this as equation number 9, or it could be written rather as in a better form, bi of z can be written as z to the power minus 1 into b I minus 1 z. By simplification, it is possible to show this, b I minus z minus k I e I minus 1 into z, okay. This we are going to call as equation number 10, okay. So, even in the z domain also you can identify what we are trying to do. It is the ith backward prediction error that we are expressing in terms of I minus 1th backward prediction error and I minus 1th forward prediction error, right. So, this is in the Z domain, it is very clear, and just taking the inverse Z transform, what we will be getting is B I of m can be written as B I minus 1 m minus 1, yes, because of the presence of this Z to the power minus 1, this 1 unit of delay. So, in the realization of the filter, we have to give that 1 unit of delay, and then this is minus Ki into E I minus 1 as it is, and here it is E I minus 1 m simply. So, this is equation number 11. Okay. Now, we have got two nice equations at our hand. One is equation number 8, the other is this equation number 11. So, these two are intermingled. Okay. The ith forward prediction being expressed like I minus 1th forward prediction, B minus 1th backward prediction, and ith backward prediction is expressed as I minus 1th backward prediction and I minus 1th forward prediction. So, that means to say, again this is a very nice iterative expression. So, that means to say that if we know a starting point, okay, we can iteratively go up to pth, and if we can go iteratively up to pth, then we solve the problem, because then I mean this is what we are realizing ultimately, that in terms of this EIM and using this BIM, we will be able to express everything. So, what is going to be our starting point? What is I? I is the order of the filter essentially, and it is the intermediate order of the filter. Okay, I mean in an iterative filtering process. So, it basically leads to an iterative filtering process. In the iterative filtering process, okay, I mean I is the intermediate order we are defining. So, our starting point could be the 0th order prediction. And what is 0th order prediction? 0th order prediction means we are not having any past value. Okay. So, in absence of any past value, what will be the prediction error for S of m? Okay. A 0th order predictor will give you a prediction error equal to S of m. So, that is the 0th order forward prediction, and 0th order backward prediction also S of m. So, let that be the starting point. So, with initial condition that we know E0 of m and we know B0 of m, okay, we should be in a position to now determine E1 of m. Can we determine E1 of m? Yes, we go back to, we now go to equation number 8. We want to determine E1 of m. We know E0 of m. E0 of m is nothing but S of m, the sample value itself, minus Ki B0 m minus 1. We know B0 m minus 1, because B0 is nothing but the sample itself, that is going to be S of m minus 1. So, essentially what we have is simply S of m, E1 of m becomes equal to Sm minus Ki, or in this case it is going to be K0 into Sm minus 1. So, how to get Sm minus 1? Give a unit delay and you get S of m minus 1. So, you can get EIM or E1m is obtained. Again you can obtain B1m, no problem, because you know B0m, you know E0, you know B0, you know E0, so you get B1. And if you know B1, in that case you will be able to determine E2, and you will be able to determine B2. and the computations are going on hand in hand. Okay. So, what is the filter structure? Now anybody getting a filter structure in their dreams? It becomes a lattice, right. So, in the filter realization, what we can simply do is that given the initial condition that E0, well, for the zeroth order prediction, given the initial condition that E0 of m is equal to B0 of m is equal to S of m, okay, we can depict these two equations, that is what we have marked with the red, this 8 and 11, this together can be depicted in a flow graph like this. You get Sn as the input sample, okay, and Sn is same as that of, or rather just telling it in the opposite way, E0 of n is same as that of Sn, and similarly B0 of n is going to be same as that of Sn. Now, what we do is that B0 of n, to that we put a delay. So, we put a delay z to the power minus 1. So, what we have over here B0 n minus 1. Okay. Now, what we want to do? Let us say that we want to get E1 of n. To get E1 of n, what we need? We need E0 of n, and we want to take B0 of m minus 1. So, now B0 of n minus 1 is already obtained from this, but not simply this, B0 of n minus 1, in this case instead of writing m we are writing n, that is not a problem, but B0 n minus 1 is multiplied by a coefficient ki. So, in this case it is becoming k1. So, we have to multiply this B0 n minus 1 by a factor k1, not exactly k1, rather minus k1. So, what we simply do is that just multiply this by a coefficient minus k1, and then we are going to add up, right. So, if we add up, what results over here? E1n. So, here we get E1n, and now let us try to get the other part, that is to say B1 of n. To get B1 of n, what we need? B1 of n, we need B0 n minus 1, we already have it, okay. At the lower arm we already have B0 n minus 1, and we also need to get minus ki E0 m, E0 n rather. Now, E0 n we already have, so what we have to do simply is to multiply that by minus k1. So, this also needs to be multiplied by minus k1. So, we multiply this by minus k1, and now we get at this end, what are we going to call? B1 of n, right. So, we have got E1 of n, we have got B1 of n. Now, this structure is going to repeat. So, just for on a completeness sake, I mean, if we are drawing the flow graph in a very formal way, we should write here as 1, 1 and all these things. So, you know that we do like that in a flow graph. So, this is E1n is available, B1n is available, and now this structure we have to continue. So, which means to say that now there will be another delay z to the power minus 1, okay, and in the next one again there will be a coefficient multiplication, but this time it will be not minus k1, instead we will be having minus k2. So, this will be a multiplication by minus k2, and in this case also very similarly there will be a multiplication by minus k2. So, in this process you will be getting here E2 of n, and here you will be getting B2 of n. Let us write it with a bracket better, B2 of n. Now, we are showing dotted lines just to indicate that a very similar structure is in progress, okay. And the last realization will be in the lattice, the last realization will be E of p minus 1 n, okay, and here we will be having B p minus 1 n, and then there will be a z to the power minus 1, and after the z to the power minus 1 there will be, okay, I mean the diagram should not appear clumsy to you. Let me just try to draw it in a clear manner. So, this will be minus Kp, this will be minus Kp over here. So, that at the end here you obtain Ep of n, and then you obtain here Bp of n. So, here the filtering ends. So, ultimately using this Ep of n and Bp of n. Now, in other words, this is also giving you the coefficients, right. So, essentially what we did, as if to say Darwin's algorithm only, okay. It is an implementation of Darwin's algorithm, then what is new thing in it, okay. We have utilized a lattice filter structure for that, okay, but essentially it is Darwin's algorithm. But what advantage is the lattice structure bringing before us? You see, in case of Darwin's algorithm, or rather that iterative algorithm which we had got, the recursive algorithm for the autocorrelation method, there we had a requirement that the autocorrelation values are to be pre-computed, and then only you will be going in for Darwin's approach of matrix solution. In this case, the two have been integrated into one. I mean, you just do the filtering in this manner, you get the coefficients. So, now what we can do is that, okay, which one is more efficient than the yes please.
K1 to Kp values?
Yes.
What are those K1 to Kp values? How to get that?
What are the K1 to Kp values? Okay. You see, this K1 to Kp values are ultimately, this is what I mean, just go back to Darwin's algorithm. Okay. What are those Ki's? Ki's etc. are the intermediate values. So, ultimately these Kp's, okay, these are going to give you the coefficients. Okay, just refer to your earlier things. Okay, ultimately see, you are not interested in EP and BP, you are interested in these things only. So, it is these coefficients that one gets. So, the first iteration is giving us the K1, the first estimate, and then the last one is going to give us the Kp. Okay. So, this K1 to Kp, we, I mean, let me go back to the old notes, then perhaps I can throw some. This is from there only. I mean, I'm just trying to take out the old slide. Anyway, I mean, this should be clear to you when we were discussing about the autocorrelation approach, that Kp. Okay, yeah. Right. Remember, I mean, this is what we were doing, K1, K2 and all these things. So, ultimately alpha 2, alpha 1, 2, alpha 2, 2, these are those values only. So, it's based on those things, right. So, now we come to some amount of comparison between these methods. Okay. Now, going in by the LPC, now the different approaches that we have dealt with so far, there are 3 approaches. So, let us make a tabular comparison. So, let us write down the covariance method here. So, this is the autocorrelation method, and this is the lattice method. So, this is covariance means that Cholesky's method, and then autocorrelation is Durbin's, and the lattice method, this is also called as the Berg method. Now, essentially, okay, this question must have come to your mind that then what is the use of the lattice structure, because ultimately we are getting these EPs and BPs. Now, the thing is that it is this errors, if we encode the errors, okay, then it is effectively getting a realization of our LPC parameters in effect. Okay, I mean, in the in one of the coming lectures, I will be also telling you about the synthesis aspect, that using the I mean LPC coefficients, how the synthesis can be done, and then this point will be more clear to you. So, we do the comparison of these 3 methods based on 2 considerations. One is the storage and the other is the computational consideration. Okay. So, we will evaluate these 3 methodologies from these 2 aspects. So, as far as the storage is concerned, let us first take the data storage requirements. Now, we normally go in for an endpoint analysis, right. Remember, in covariance method also we were truncating the series to n number of samples. In autocorrelation method also we were having n number of samples, and lattice also ultimately whenever we are inputting the samples, there is a certain finite number of samples that we are making into the system, bringing into the system. So, let us call that those things as n, but because there are 3 methodologies, the number of points that we will be requiring may not be exactly the same in these 3 approaches. So, data wise, let us call that, say, covariance method has got in 1 number of points, autocorrelation method has got in 2 number of points, and lattice method that has got in 3 number of points, but in fact it will be 3 times n3. And do you know that why it is 3 times of n3? Okay, because we also need to have the errors, okay, to be stored. Okay, so this is the, so here it is 3 times of n3, and then the matrix. So 3 times of n3, because you have to store the data, you have to store the forward errors, you have to store the backward errors. Matrix, here it is proportional to p square by 2, okay, and in the case of autocorrelation it is proportional to P, and there is no matrix storage that will be required in lattice method. So, here the question does not arise. Regarding the windowing, covariance method uses 0, autocorrelation uses N2, and this does not require any windowing. Okay. And for the computation of windowing computation, here there is no windowing that is involved in the covariance method, whereas in the autocorrelation indeed the windowing is there with N2 number of points, and in the lattice method there is no such windowing concept. And then regarding the correlation, okay, for correlation the covariance method has the correlation computation proportional to N1 into P, and here for the autocorrelation method it is N2 into P, and there is no correlation computation for the lattice method. But for the matrix solution, so that means to say that for the matrix inversion, here this is proportional to, covariance method is proportional to P cube, right, very heavy computational burden, whereas autocorrelation method is proportional to P square, okay, and lattice method has got 5n3 times P. In fact, this follows from the algorithm. I mean, we are not going into the exact derivation, but it is just to give you an idea about what sort of storage and computational comparisons one gets by comparing these three methods: covariance, autocorrelation, and lattice method. Okay. Yes, please.
Sir, in the lattice method with respect to correlation,
Yeah.
there should be the values of KIs. In the lattice method, we use values of KI, and these values of KI depend on the autocorrelations. So there must be computational complexity involved with respect to correlation calculation also. N3P proportional to N3P.
Proportional to no, there is no correlation computation that is done. Okay.
How will we get the value of KI? Because to calculate KIs we require correlation coefficients.
Okay, I suppose that this aspect I will throw some more light on it. I'll be explaining this. In fact, correlation is not required, but how one can get an idea of this KIs, okay, this aspect I will talk of in the coming class, because we are already coming to the end of the time for the present class. So thank you for now.